Let's start the topic of the Carnot cycle. So before going there, this is a general understanding about the heat engines or the steam engines. The steam engine is a type of heat engine. Okay, so the heat engine encompasses different kinds of like steam engines, diesel engines, gas powered turbines. So all these kinds of different engines are basically a variety of a heat engine. Okay, now what's a heat engine basically doing is the concept is extremely simple. So you're taking heat from a high temperature source and you're trying to convert that heat into work. Okay, so say you get some heat in form of some steam, and when you get that steam, you are using the power of that steam to move a piston to do some work, the PV work, the expansion. Now that entire heat cannot be used to do some work. So some of that will be used to do some work. The rest of the steam that is left is being then delivered to a low temperature reservoir, and then you do that process again. So you get heat, convert some of that heat into the work, the rest of it is going into waste, and you are just using the rest of that steam that is left into, and you're just moving it into a low temperature reservoir. So this is basically the heat engine. Now, as we discussed before, the whole concept about the heat engine now is to understand if there is a theoretical limit to the efficiency of the heat engine. Now, what is an efficiency? Efficiency is basically the ratio between the work that is being done to the amount of heat that is being supplied. Okay, and this equation is 36. Okay, so we are trying to find out if there is a theoretical limit to the efficiency of heat engines. Now, there were many scientists, many people who were trying to come up with an answer to this. The person who came up with an answer to this was Sadi Carnot, and we are trying to understand how or what he exactly did, like how did he come up with that explanation. Okay, so we are trying to understand the Carnot heat engine. So a heat engine which Carnot designed, a hypothetical heat engine, and that was basically a closed loop system. Okay, there was a closed process, like it was a in the PV diagram, if you draw that will be a closed process. So that's why we have a cycle, we have a closed cycle. So that is why we also call it the Carnot cycle. So it's a closed system, it's a closed process. All the steps that were there are assumed to be reversible with ideal gases. So basically, he was trying to come up with the hypothetical best case scenario. Okay, that does not mean that we will be able to make a Carnot cycle, but hypothetically we are trying to approximate our real world heat engines to a Carnot cycle, to a Carnot heat engine, right? Because if Carnot heat engine is the best we can get, we are trying to emulate that in the real world. But we are trying to see what is the efficiency of that hypothetical best case scenario. So we will be doing that in the Carnot cycle. Now, the Carnot cycle is being drawn here. It's the indicator diagram in which you have the PV, and this process in which you are going. So this is there is some system which is a closed system, and all the processes will be reversible, and you have an ideal gas inside it. It's a hypothetical, but let's assume that this is happening. And so this is system A, which has a particular pressure, volume, and temperature. Okay. Now, and you assume that there is 1 mole of the gas or the steam that we are considering 1 mole. Okay. So we know the system in here, and this system is going to B, then this system is going from B to C, then to D, and then back to A, and that's why we have a cycle in here. Now, Process A is basically an isothermal process. So process when you're going from A to B, this is similar to how we studied the first law and when we were studying the different types of special cases. We were trying to see like, okay, when we are going from A to B, so this is a isothermal process. And what is happening? We are increasing the volume. So the process 1 is basically when you're moving from A to B, this is an isothermal expansion. So this is step 1. So this is isothermal expansion, okay? Now when you're moving from B to C, this is also an expansion, but this is not isothermal anymore. This is adiabatic, right? And in here you can see that this process is like more steeper, right? We learned before that generally isothermal and adiabatic, if you see the general tendencies of these two processes, adiabatic will be more steeper than the isothermal. So in here it's more clear that this step 2 is an adiabatic process, okay? An adiabatic process which is going in expansion to step 2 is an adiabatic expansion. Now steps 3, which is going from C to D, is again an isothermal process, but in this case this is compression. Similarly for step 4, when you're going from D to A, this is an adiabatic compression, okay? So we'll be trying to find out everything that we can about this hypothetical cycle, okay? Now, in here, we will be studying each of these 4 steps individually, and we are trying to find out the heat exchange in each of the steps. Like what was the heat that was given? So if there was a heat given, what was the work that was done? And what was the change in internal energy? Things like that. So for each of these steps, we'll be trying to find out, we'll be again going back to the first law of thermodynamics, and we'll be trying to find out the Q, the W, and the internal energy. And when we have all those variables for all these, then we'll be trying to find out the net work done, the net heat exchange, and the net amount of internal energy in this whole process. Now, since you have gone through this process once before, we can right now say that the change in internal energy will be 0 when it goes from A to B and then again come back to A, because internal energy is a state function. It will only depend upon the initial and final state. So if it starts from A and then goes back to A, then the initial and the final state is the same. The internal energy won't change. Brilliant, it won't change. But in here, we know that Q and work, so the heat and the work, they are not state functions, they're path functions. So they won't be, their summation won't come out to be 0. So there will be some amount of work done and some amount of heat exchange when we are done with the whole process. So our whole motive is to find the Q and the W, because if we find the Q of the whole cycle and W of the whole cycle, and this being a hypothetical best case scenario, we will be able to find out the hypothetical best case scenario for the efficiency of such a heat engine. Okay, so let's start off with understanding the heat engine. So all processes are reversible. Best case scenario, all processes are reversible, and we have 1 mole of steam. Okay, to make things easier, we'll just take 1 mole. Okay, and let's assume that you have a piston. Okay, and you have 1 mole of steam inside this cylinder, and when you are giving it heat, then this gas inside is expanding and things are going on, and we'll be studying this system in terms of this. Okay, later on we'll see that the choice of the gas inside will not matter. Okay, whatever you take, the efficiency of the steam engine will not depend upon whether you use steam or air or any other gas. Okay, but we'll see how that happens. So we'll see that the final thing that comes in this equation is not does not refer to any of these material properties of the gas that is inside. Okay, so let's move to the first step, which is the isothermal expansion. Volume, as you can see, is increasing. So this is an isothermal expansion. So let's try to find out what is going on in here. Very straightforward. Since dt is 0 by definition, because this is isothermal, dE comes out to be 0, right? Because the temperature doesn't change, the internal energy won't change. So when the internal energy is not changing, we know that the first law is this. So if this is the first law, this is not changing, so dq is basically dw, right? So dq is basically dw. So we have seen this earlier, how to find out the amount of work done when we have an isothermal expansion, okay? So quickly we'll be seeing that. So if we integrate this, you will get w, right? So we are trying to find out w. So w is basically p del v moving from VA to VB, right? Now, remember that the P in here is also changing, but we have to substitute the value of P in terms of V. So since this is an ideal gas, so everything is behaving like ideally, PV is equal to nRT holes in here, and n being 1, PV is RT. So P is RT by V. So in here what you get is RT by V dV from VA to VB. Now this becomes, so the work in here, becomes RT ln VB by VA, okay? And the temperature here was constant, and that was the temperature of the heated temperatures, right? So this is represented by H in here, okay? So when you have the higher temperature, this is the hotter temperature is the TH, and when we'll have the colder temperatures, we'll be representing that with TC. So this is the work done, and we exactly know that this will be equal to the Q of the system. Why? Because the delta E is equal to 0. Okay, so let's make this equation 37. It's pretty simple, right? It's just an isothermal expansion. We have done this before, so we get this. Okay, now we move on to step 2. Now step 2 is an adiabatic expansion, but so just by definition we know that the Q is 0, right? Because this is an adiabatic, the Q is 0. So when Q becomes 0, the first law comes out to be something like this, right? Because the Q becomes 0. Okay. Now, when this is an expansion, right? So the dq, so the dw, since it's an expansion, dw in itself is positive because it's expansion. Expansions means positive work. But in here, the dE will be negative of that positive, right? So it will be negative. That means the system will cool, right? Because it is expanding and the dE is the negative of that positive work. So negative of that positive becomes negative, and once dE is negative, that means the dE is decreasing, and when dE decreases, that means temperature decreases, and therefore temperature decreases, that means the system is cooling, right? Okay, so in here it becomes dE. So okay, let me write down here W1 to say that this was 1, okay, just for keeping it that way, and in here this is W2, okay? Okay, so E2. Now we have studied before that CV was dE upon dt at constant volume. Okay, so what this becomes is dE becomes CV dt. Okay, so this becomes CV dt. Now, the dt in here is, it came from a hotter temperature to now it came to a lower temperature. So this is dE. Okay. If this is dE, what is dW? Because dQ is 0, right? So dQ2 was 0, dE2 is this. What is dW? So dW2 will just become the negative of this, right? So it thus becomes the negative of this number, this value, T hot minus T cold. Okay, now we will get this as equation 38. Okay, awesome. Now, similarly, we move to the isothermal compression example. Okay, now when you move to the isothermal compression, again the dE becomes 0 because it's an isothermal reaction. Isothermal means there is no change in temperature. No change in temperature means no change in the internal energy. Okay, so this becomes D3 equal to 0. Similarly, this whole thing behaves similarly, and dQ will be, dQ3 will be equal to dW3. So we just need to find out dW3 in here. Now, how will you find out dW3? Okay, so you integrate this to get the W3. So I'm just writing it here. Again, you do a P del V, right? So you do a P dV, and you're going from Vc to a Vd. Okay, so you are doing this. Now, again, changing PV, using PV equal to nRT, so this will become RT by V. Okay, so this again will become RT, and the T being T cold because it's the colder temperature now, RT by V, so this will become dV by V, and when you integrate that, it becomes Vd by Vc. Okay, now this is represented as W3, and I'll name this equation 39. Okay, Q3 will be exactly this. Okay, so Q3 is equal to W3. So this is exactly the same value as the Q3. Okay, now let's go to the adiabatic compression. Now, adiabatic compression again will be similar to this, in which the dQ4 will be equal to 0. Why? Because by definition it's an adiabatic process. Now, since it is a adiabatic process, so dQ becomes 0. Again, the relationship between this will be something like this. Now, in this case, your W4 is a compression, right? So W4 is a negative work in here. Okay, so when you're doing negative work in here, so negative times this negative will become positive, and therefore the internal energy of the system will increase, right? So if the internal energy of the system is increasing, you're getting hotter. So you're moving from a colder temperature to a hotter temperature, and this means that you're getting hotter. Okay, in this process, in this step, you're getting hotter. Okay, so let's now just calculate similar to this. Let's calculate the change in internal energy. So the change in internal energy similar to that will be CV dt in this case. So CV and delta T is basically, so you're becoming hotter minus the initial colder. So dE4 is basically this, and your W4 will be just the negative of this, CV T hot minus T cold. Okay. Now, when we have the individual dEs, dQs, so you have Q1, Q2, Q3, Q4, W1, W2, W3, W4, and for all these steps, what we'll do to calculate the net, we'll just be adding these up. Okay. So in the next board, we'll be just adding these all equations. Okay, to find out the net of this Carnot cycle.